Okay, we can start our today's lecture in our. Okay, so convolutional neural networks is kind of the neural networks. Specifically, we call one of the deep neural network architecture based on the convolution operation. And this is one of the famous architecture of deep neural networks. The convolutional neural networks specifically perform better in image classification, object recognition, this type of work. Firstly, it was proposed only for that, but later, actually, convolutional neural networks also used for the text data processing and also the numeric data processing, signal processing. That means each and every dimension of our data science. So the part of this lecture is adapted from the CS 898, University of Waterloo, Canada. So at first we need to understand that is the types of our learning models. So usually if we divide our learning models in two dimensions, like in X and Y. In X-axis, if we put the shallow and deep, okay, so that means we can see here there is some of the architectures are shallow architecture learning models, and some of the architectures are deep architectures in those learning models. And in y-axis, if we put the supervised and unsupervised learning models, then we can see that some of the learning models we will see those have the shallow architecture. They follow the shallow architecture but supervised, like the perceptron, support vector machine, boosting. So those algorithms are we call the shallow architecture and also the supervised approach. Okay, supervised approach. Uh, Now, if we consider about like the that is the deep architecture and supervised. So some of the machine learning models you can see that. So deep architecture, that is neural net, it is deep neural network actually. The deep neural network architecture. We can say convolutional neural architecture and recurrent neural network. So those are our supervised model, but they follow the deep neural network architectures. And some of the architectures are shallow but unsupervised. They follow the unsupervised approach, like the encoder neural networks, and also sparse encoding, restricted Boltzmann machine, and Gaussian mixer models. So those followed the shallow architecture, but those algorithms are unsupervised. Okay, unsupervised, follow the unsupervised principle. And some of the algorithms you can see they have the deep architecture and followed the unsupervised philosophy. Okay, then that is the deep autoencoder and deep belief network, Bayesian non-parametrics, SP. So those are our uh, those follows the deep architecture, but usually also followed the unsupervised principle. So here we can see that there is convolutional neural network. The convolutional neural network is, today's discussion we will discuss about this. It is supervised approach, but it will follow the deep principle. That means there will be many layers in our neural network, convolutional neural networks. So before understanding the convolutional neural networks, we need to understand why the convolutional neural networks is necessary, and what's the benefit of using the CNN, convolutional neural networks. So generally, we know that there is the If we have the small model, it's good to learn. A small model, you can learn it easily, and also even though you have very small device, then you can maybe um, still that is you can learn your model on your 10-year model on very small devices also. That means no need to use some powerful machines for that. But usually the neural networks, traditional neural networks, or you can say deep neural network architectures, they have the fully connected models. So like here, one of the neural network architectures. So this is a neural network, just neural network architecture. But we can see it has many hidden layers, like 1, 2, 3, just 3 hidden layers. So that means we can say it deep neural networks, and we can see that uh, here we can see this in our input layer we have 8 neurons, and hidden layer 1, hidden layer 2, hidden layer 3, we have 10 neurons, and in output layer we have 4 neurons. So for a fully connected network, that means each of the neurons of input layer, it should connect each of the neurons of hidden layer 1. So, and also similarly, each of the neurons of hidden layer 1, it should connect each of the neurons of hidden layer 2. Again, each of the neurons of hidden layer 2, it should connect each of the neurons of hidden layer 3. And finally, each of the neurons of hidden layer 3 must connect also each of the neurons of output layer. So this is called fully connected model. Fully connected model. So that means we can see that even though we designed a simple neural networks, just only 3 hidden layers, and each and every hidden layers we have placed the 10 neurons. Then we can see lots of connections are there. Lots of connections are there. Connections means edges. Edges means weights. That is, weights means the learning parameters. Okay. So that means even though we have very simple, very small neural networks here, but um, there are many actually. There are many connections. That means we need to learn many parameters. So if we want to calculate, that is how many parameters we have to learn here, then we can see in this case 10 neurons. Each and every one is connected to another, 8 neurons in the input layer, 8 neurons in input layer. And then in this layer we have 10. So that means we can say for each and every neuron, one neuron will connect to 8 neurons. So connect to 8 neurons, one neuron. But we have 10 neurons, okay? 10 neurons in this layer, 10 neurons. And we can see each and every one is connected to 8 input layer neurons. So here, total connection here, we can see 8 times 10, that is the total 80 connections. 80 connections means we have to consider, that is, for each and every connection, we have to consider the weights. So that means total 80 weights here. And then again, we can see from this layer, that is 10 neurons, here is also 10 neurons. So that means 10 times 10. These much connections we have. And here we can say again 10 times 10. This many connection we have in layer 3. And then we can see here there is a 4 neurons, and each every neuron is connected to 10 neurons. Okay, so that means we can see total number of connections or total number of weights, even if we consider just simply without bias. So here is 80 plus 100 plus 100 plus 40. So that means the learning parameters we need to learn for this neural network is this much. If we consider the bias, then it will be more, like for this we have to consider 10 bias plus 10. because each and every hidden layer we have to consider a bias. For here also plus 10. For here also plus 10. And for this layer, we have to consider extra 4 biases. So that means if someone asks you that is how many parameters you have to learn for this neural network model, then you have to think about that is these are the number of parameters we need to learn if we consider the fully connected neural networks here. Okay, so that means that's huge. If we consider about not only the 4, but we can see sometimes the number of neurons in each layer may be 100, and also we need to consider maybe 100 layers also, or 25 layers also. That means huge number of learning parameters we have to learn. So the consideration here is that is, can some of these be shared? That means we can see that currently in deep neural network architecture, no weight is shared. Like this weight, if we consider this weight as W1, actually this weight is used only here, only here. Okay, so that means every weight is different. None of the weights are shared. So can we design something that is where we will see that is the weight is shared among different maybe neurons? Then if weights are shared in different neurons, then number of weights will be reduced, or we can say number of learned parameters will be reduced. And another thing is actually, so we have here fully connected model. Are all these connections necessary? Okay, so that means if we can reduce some of the connections, then maybe it's better. Uh, then we need to learn less number of parameters. Okay. Uh, so here we can consider like for an image categorization, or we can say for object detection, or we can say uh, for just object classification. Like this is an image. In this image, we have a bird, and we want to recognize this whether this one is bird or maybe not, or we can say which kind of bird is this. Okay, so for recognizing the pattern of this image, recognizing the pattern of that bird, some part of this image may be no information, like here. In this case, no information is there. In this case, no information is there. Okay. So can we represent this one using some small region, and so that we can learn with the fewer parameters? Like we can say, can we detect uh, something like the beak of this bird? Can we detect something like the legs of this bird, the wings of this bird, tails of this bird? So if we can consider something like one beak detector, one wings detector, one leg detector, one tail detector, then that will be enough actually to recognize this bird. That is, what type of bird is this? Or we can say whether this one is bird or maybe animal. Okay, so some patterns are much smaller than the whole image. So we can see that the whole image is this, but to recognize one bird, we need to maybe consider the beak of this bird, eye of this bird, wings of this bird, tail of this bird, legs of this bird. So if we can correctly recognize the features of beaks, correctly recognize the features of legs, correctly recognize the features of eyes of that bird, then we can easily discriminate from one bird to another bird. And we can see here that is actually the information, or we can say that the discriminative features lies only within some portion of this image, not the whole image, then why the whole image is necessary for our consideration? Okay, so that's why here we want to find out maybe something like the beak detector, find out the wing detector, leg detector, tail detector, eye detectors, those kind of detectors we want to find out. And if we can find out those, then there is uh, the size of our learning model will be smaller, and we can have lower or very smaller number of parameters also. So, but the problem is, so consider here that we can see that is beak is in this position, but for this bird, the beak is in another position. So we can see here the beak is in uh, the upper left corner, but this one is the middle of the image. So what should we do? To find out the beak, we have to scan through all these images. That means we can say this is our beak detector, this is our beak detector, that it needs to search the whole image for the beak. Here is also the same. Okay, so that means we can see that this is the upper left beak detector, this is the middle beak detector. Okay, and then we can compress the same parameters. Okay, that means we can say the same parameters or weights we can use for those. Now, so from this discussion, what we have learned that is, instead of considering the whole image, we have to consider the part of the image where the information is stored. And for that, to recognize some of the objects or some of the animals, some of the birds, what we need to do, maybe some of the portion we need to recognize, and those kind of detector we need to design, and that detector actually will help us to detect the important part of that object. Like here for this bird, we want to detect a beak detector. For this bird, we want to detect the eye detector. For this bird, we want to detect the leg detector, tail detector, like this wing detector. Okay. So that means we need different kinds of detectors. Now move to our that is the convolutional neural networks. So here we can see that if we consider this is our image, so this is our image, this is our image, and here this is our beak detector. This is our beak detector. So this is our beak detector. So this beak detector in convolutional neural network models, we can call it as a filter, or sometimes we also call it kernel. So that means this kind of detector, this beak detector is a filter, and that will try to find out the beak in these images. Okay, and again, as I already mentioned, that there is sometimes the beak will position at the maybe left corner, sometimes at the middle, sometimes at the lower corner. Okay, that means different position. That's why we need to search the beak throughout these images. Okay, so here is the filter, and now uh, for finding out our important information, or we can say important features, what we have to do, we have to apply some form of convolution operation. Convolution operation. That means uh, if we divide these images in several patches of the same size of the beak detector, then for each and every patch, and here the filter, we have to apply some form of convolution. And then the convolution, the output of the convolution will be the feature. Okay, will be the feature. So that's what we want to do here. So a convolutional neural network is a neural network with some convolutional layers. So some convolution layers are there, and some other supportive layers also there. So a convolution layer has a number of filters that does convolution operation. Okay, So that means we can see here one of the filter we introduced, that is called that is the beck detector. Similarly, another filter we need to introduce, that is the eye detector. Another filter we need to use, that is the maybe wing detector, leg detector. Okay. So that means several filters we need to introduce for finding out the several important features. So the one of the whole procedure can be like this. That means we can see here that in our convolutional neural network model, we have like at first the convolution layer. As I already mentioned, there's several other layers in convolutional neural networks also. So at first we can see here that is the convolution layer. Okay, convolution layer. So the architecture, the whole architecture is here. At first, maybe we need to consider the convolution layer. This is the main layer in our convolution neural networks. And then after that, we need to apply the maybe the pooling. Okay, the pooling. That means it's kind of sampling, or we can say that is the compressing layer. So like here, the max pooling is one of the pooling operation. And then again, we have to apply the convolution another time. Okay, so we can see this is the first convolution layer, the first convolution layer, and then after subsampling, we applied the convolution again. This is second convolution layer. Okay, and then again we can see here the pooling. Okay, in this way we can have many convolution and pooling layers stacked. Okay, and after that maybe finally we can say we have flattened. After flattening, we will discuss about each and every component here. After flattening, then we will pass this flattened features to a fully connected neural network. So this is the fully connected neural network. That means we can see this part is fully connected neural network. So this is a neural network, whatever we discussed in our maybe last two classes. So that's the fully connected feed forward network. And then we can see here it is finally it will classify as the cat or dog or something. Okay? So here is the image of cat. Then it will classify finally maybe the cat. So in this case, we can see this part is actually the neural network. This part neural network. So it will perform the classification operation, and rest of the part, specifically this part it will use for the feature extraction. Okay, so this part it will use for the feature extraction. As I already mentioned, that means for each and every convolution operation, we have to consider several filters, and each and every filter will responsible for finding out the features, like the features of beak, the features of eyes, features of legs, features of tails, like this. Okay, so here is this. Maybe you can say one of the that is the filter. It will find out the features of ears, and we can say the features of nose and eyes. Okay, so several detectors we need to introduce. And in this case, we can see here the first convolution layer, it will try to extract the surface level features. And then maybe the second convolution layer, it will try to find out the depth level features. So that means from surface to depth. So different kinds of features it will extract. So this part is
না
actually
একটু সারফেস লেভেল ফিচার কি ধরনের হতে পারে আর ডেপথ লেভেল ফিচারের এক্সাম্পল যদি দিতেন তাহলে বুঝতে সুবিধা হতো।
okay. Okay, I will explain that. Okay, in another picture we have. So some of the surface level feature it will extract here, and depth level feature it will extract in depth level of convolutions. Okay, we have those here. You can see surface level and depth level here. You can see that. Like this is a car. Okay, so if we can see that this is for the low level features or surface level features. here we can say just only the textures, okay, just only the textures it has, like the different shapes and colors, and then we can see the mid-level features here and then high-level features here. That means for in this case we can say uh, the more representation or more in-depth representation features are there, more in-depth representational features, okay, not only the lines or colors. We can see here different textures and their patterns also there. Here is in-depth also, more in-depth patterns we need to recognize. So that means from here, from this for this car image, if we apply the first convolution, after the first convolution, if we display the convolutional results, then this kind of results you will get. This result you will get from our there is the fast filter, we can say, like the brake detector or something. For this case, maybe you can say um, uh, the body of the car detector, okay, the wheel detectors, okay. So, there are several filters will extract the several kinds of features. Like we can say there is surface level features in this case. Just only it will detect some kind of the lines and also colors. And then in depth level features, it will try to find out the textures, okay. And then more depth level textures it will try to find out. Is it clear?
Yeah, sir, on a high level, but I think একটু ম্যাথটা
Hmm? High level.
একটু হাই লেভেলে আইডিয়া পেলাম স্যার, বাট একটু মনে হয় আর কিছু দূর গেলে তা আরো ক্লিয়ার হবে।
Okay. Okay, so that means this part it will consider our you can say it will consider our feature extraction, and this part actually for our classification. So now this part is for the feature extraction, and this is here is fully connected neural networks. So this is for the classification purpose. Sometimes you will find that in our many neural network models nowadays, uh, this part is replaced. That means this classifier is replaced by some other classifiers. Even we can say there is the fusion of CNN and also the SVM. So you can fuse these models. We can see actually this part is for the classification. So instead of the fully connected neural networks, we can apply some form of our machine learning, uh, our machine learning classifiers here. Okay, because up to this we are just finding out the features. So instead of fully connected neural networks, you can apply some other classifiers also. Okay, so uh, so the main purpose of CNN is actually the feature extraction. The feature extraction, okay. Uh, uh, how we can find out the discriminative features and in-depth features also, okay. That is depth level features also. Okay, so there are several architectures in CNN. Usually, I think many of you already heard about those models like the VGG, FastNet, then MobileNet, then Inception. So all those are different architectures of CNN. And different architectures of CNN also used for the object detection, like we can say YOLO V3, V5, V9. Okay, so those are the for object detection, faster RCN and CNN. So that means different architectures of neural networks we have. That is convolutional neural networks we have for different purposes. So one of the linear architecture is this, that is input image, then apply the convolution, and then apply the non-linearity here. Non-linearity, it means that some form of activation function we need to use. The popularly used activation function in convolution and neural network is rectified linear unit, and the model is this. Okay. Uh, so in this case, we can see that is after non-linearity, then the spatial pooling. Okay, so that means you need to perform pooling operation. There are several kinds of poolings also, like max pooling, min pooling, average pooling. Okay, so the pooling operation, and then we can do the normalization. That means we can perform some standardization operation uh, to normalize those values also, and then we will get the feature maps. So that means we can see that, so input image after performing the convolution operation, then these are the kind of pre-processing. Okay, kind of pre-processing. We do some pre-processing, like the for our general feature extraction. After they extracted the features, we do some pre-processing on the features. So we can apply the same kind of pre-processing also in our convolutional neural networks, and then we will get the feature maps. And from these feature maps, again, what we have to do, we have to perform maybe the convolution operation. Okay, convolution operation. So in this case, again, for the nonlinearity, you can use the sigmoid. Sigmoid is specifically used in neural networks, and the sigmoid popularly used in the shallow neural network architecture. But in deep neural network architecture, popular use is the rectified linear unit. Okay, so there are many versions of also the rectified linear unit. ReLU, Licky ReLU. Okay, and another our function is the 10H. It is not so popular, but we can use that one. And here is the sigmoid also. Okay, and this is our ReLU. So the rectified linear unit, this is specifically most popular in our convolutional neural architecture. And another popular one is softmax. So there are several versions. You can propose that is your neural network by yourself. Okay, so that means proposed convolutional neural networks by yourself for your application, and therefore you will see that for many applications, many neural networks, convolutional neural network is proposed by the username, okay, or the application name. Um, for the garbage classifier, if someone can mention that garbage CNN. Okay. So they can just mention like this way. Okay, so that means you can design the customized CNN model for your application, and you can name it according to your name. So simple model, you can say the input and FC, that is the a linear classifier, the fully connected layer. This is just only a neural network. And then we can see the input, convolution, then ReLU, and then fully connected. So this can be another model. The input and then the convolutional layer, then the ReLU, that is non-linear, and then we can see here is the FC, fully connected neural networks. And someone can design like this: the input and then convolutional ReLU and pooling, here is the 2 times, and then fully connected layer, and then ReLU, and then again fully connected layer. So this can be another model. This can be another model. That means we can say we have the flexibility to use these things, like not only the that is convolutional, then pooling, like this way. We can apply in different ways, like convolution, ReLU, and pooling 2 times, and then fully connected. Again, we can apply ReLU, and again we can apply the fully connected layer. So another variation can be like input, convolutional ReLU, and convolutional ReLU and pooling. Okay, so we can see that convolution, then ReLU, and then then convolution again. Usually, what we do, like convolution, then ReLU, then pooling. Okay, but we can see that there is the pooling operation we performed after that. That means convolution, ReLU, then pooling. Okay, so that means it is not strict also. That means you have to apply the pooling operation after every convolution operation. Okay, so no need to do that. We have the flexibility in designing our convolution model. So and then you can see there is the FC, fully connected layer, and ReLU 2 times, and finally again we can move to the fully connected layer. So that means different variations we can try, and according to your model, maybe for to solve your problem, maybe that will be perfect for you. Okay, so so there is no hard and fast rules for here. That is, you have to perform like convolution, after that pooling, after that ReLU something. No, so you can design your model by yourself. Okay, so I have already discussed this one. Now we have to think about that is the convolution operation. Okay, so convolution operation we can perform like, maybe we can say there is in one-dimensional features or two-dimensional features, three-dimensional features. So here specifically the convolution operation, you can see that is if we have two functions f and g. So usually we write like f times g, or f convolution g is defined the integral of the product of two functions. Integral of product of two functions. So here one function is f of tau and another is g of t minus tau. And here is the d tau. And we can see here this is the integration. Okay. So integral of product of two functions. Here one function is this and another function is this. But what we have to do, this function, so two functions, after one is reversed. Okay, that means we can see this function is reversed here. G is reversed and shifted. Okay, so we have to do some form of shifting. So this is called our convolution operation. For example, if we have here like one is f and another one is g. So this is one function. The values are like 1, 4, 2, 5. And g, we have another function that is 3, 4, and 1. Then what we have to do, we have to find out the 1D convolution, and this will be the result. Okay. To perform the operation, convolution operation, we have to reverse one of the function. Let's say we want to reverse the g. So here is f is f. So f is, this is the f. And we can see g is in reverse, then it will be 1, 4, and 3. Okay, so here is this 1, 4, and 3. This is our g. So this is f and this is g. So now what we have to do, we have to apply some convolution operation. Here is multiplication actually, and then we have to shift. So at first we can see that that is for 1, 4, and 3. 1, 4, and 3. Here 3 and 1 we have to perform at the fastest stage. Okay, so first phase, that is C0, it will be 3 times 1. So 3 times 1 is 3. And then we have to shift the G shifted. So if we shift that one, that means we can see now 4, 3, and 1, 4. Okay, so now we can see the common part here is 4, 3, 4, 3, and 1, 4, 1, 4. Here is 1, 4. Perform the operation, then we will get the 16. And then again we have to shift one of the functions. So that means we have shifted, and we can see here this is 2 times 3, then 4 times 4, and 1 times 1. So we will get this value, that is 23. And we have to shift again, then we will get this. And then we can see here 5 times 3, 2 times 4, and 4 times 1. So here is this, then 27. And then again we have to shift it this one, and then we can see the 5 and 4 and 2 and 1. After that we have to shift again, and you can see 5, 1. So that here is the 5, 1. And finally after that we have to shift again. On if we shift, then we can see those are actually no common elements will be there. So this will be the result of our one-dimensional convolution. Okay, if we conclude two functions f and g, so this will be our result. If we apply the convolution operation on two-dimensional data, like here, if we consider our 6 by 6 image, and in this case, this is one function. If we consider this is our f, and then we have to think about the g. G is our kind of the filter. Okay, so g is a filter, kind of filter. So if we consider this is our g, then for the convolution operation in 2D, two-dimensional features, what we have to do, we have to divide this image into the patch. So we can see that is the patch should be the same size of the filters. In this case, the filter we consider that because of 2D convolution, the filter is row. It has row and column. That means 3 by 3. Okay, so 3 by 3. So we have to divide this image. At first, consider the 3 by 3 patch. So here is this. Okay, so that means this is 3 by 3. 3 by 3. Now here is the 3 by 3. Here is also 3 by 3. We can perform the convolution operation, and to perform the convolution operation in this case, we can see that for the first first phase, that means you can say this is our 3 by 3, and here is our filter of 3 by 3. Then we can see that uh, if we do the convolution operation, it is a 1 times this is the 1. So 1 times 1 is what? 1 times 1 is 1 times 1. So 1 times 1 plus of negative 1 times 0. So negative 1 times 0, sorry, 0, and then plus of, here is the negative 1, here is the 0. That means negative 1 times 0 plus of, here is the negative 1, here is the 0. Negative 1 times 0 plus of this one, here is also 1. Okay, so operation will be like 1 times 1 plus of negative 1, here is 0. So negative 1 times 0 plus of, uh, here is also negative 1, here is 0, negative 1, and then 0 plus, then the negative 1 here again. You can see here is a negative 1, and here is a 0. So that means negative 1 times 0 plus of 1 times 1. Okay, here is a 1, here is 1. 1 times 1. Okay, now what we have to do, we can see that this is 0, this will be 0, here is 0, this one is 0, this one is 0. Okay, so this is 1 times 1 is 1, plus of here is 1 times 1 is 1, plus of 1 times 1 is 1. That means total we can see 3. Okay, so we have 3. That means after performing the convolution operation in our here is the first patch, and our there is a 3 by 3 filter. So 3 by 3 filter. If we perform the convolution operation, then output will be 3. So here is this. We can see that at first we got the 3 here. And then what we have to do, according to our discussion, actually, if we consider this filter 1, this is our bake detector. So we have to search the bakes throughout the image, okay, throughout the image. So what we have to do, we have to shift. So we have to shift that is the patch. Okay, so that means here is the if we shift here, for the shifting there are several types of things we need to consider. That is, so can we can just do the 1 bit shifting, or we can say 2 bit shifting. Okay, uh, so in this case, this is called the straight. Okay, straight. That means how many bits you want to shift at a time. So we, in this case, a straight one. That means you want to shift just 1 bit. After that, again we need to form the patch. So this time this is our patch. That means it is 3 by 3. And again we have to apply the operation with our, that is the filter, the bake detector. Okay, bake detector. And then perform the convolution operation here, then we will get the negative one. In this way, we have to, maybe you can say, after shifting one bit and every time, then we will get like the next shift, we will get this patch. And for that, we will get one value here. And after that, maybe we need to shift again. So here we will get this patch. And for that, we will get another value here. Then what we have to do, we have to uh, that is apply some downshifting in this case, and again one bit. Okay, one bit, that means we can see if we downshift just one bit, so this will be our patch this time. This will be our patch. And again what we have to do, we have to just perform the convolution operation, then we will get this, that, that, and that value. And after that we have to again apply the downshifting, and for that we will get, this will be our first pass for that case. So that means we will get again the values here, there, there, and there. And then again what we have to do after that, we have to do some downshifting, and then this will be the case, this will be our pass. So on that case we will get like, so that means we can see that if we consider our convolution operation, if we consider just only one filter here, and that is the straight one in this case, then the output will be this. Okay, output will be this. So this output, this is the output. Usually we call this one is also feature map. Okay, feature map. So that's our the conclusion output of, if we apply in 6 by 6 images and considering this one filter. Okay, so this is the output of our conclusion. Similarly, what we can do, we can apply another filter. So another filter means, like if we consider about the wing detector, then this is our wing detector. Okay, so filter 2 is our wing detector. And again, what we have to do, we have to perform the same operation, uh, and also the considering the same philosophy, but the different filter. Okay, different filter, because this is the different detector. We want to find out or search now the wing. Okay, and that's why maybe you can say that is we applied another filter, filter number 2, and for that we will get another feature map. You can see here, here is the foreground one and one is the background. The background one is for our filter 1, and we can say that the front one is our filter from the filter 2, filter 2. Okay, now if we have like the color image. Okay, so color image. So usually if we have color image, then specifically in that color image, we have three components are there. One is red, green, and blue. I think we know those things. So that means from a color image, we can, if we read that, then usually we get three panel. One is for red, another is for green, another is for blue. And here is, we can see that we have like, for the same image, for the same image we have three channels. So these are the three channels, and for each and every channel we will get different values. Okay, so this panel is for red, this panel is for green, and this panel is for this panel is for blue. Okay, then what we have to do, so we have the filter 1 and here is the filter 2, and we can see that that is for the filter 1 we have to apply this filter 1 and this filter 2 we have to apply this one. Okay? One for the red channel, apply another one for the green channel, apply another one is for blue channel. Okay, so color image, for the case of the color image, if we have usually we have the 3 channels. So on that case, we have to apply filters to each and every channel. Then the next thing what we have to learn actually that we can see here. We can see here that is, if we consider this filter of 3 by 3, this is the filter size, and if the image size is 6 by 6, and if we consider that is the straight one, and also we can say no padding, we didn't do padding here, then the size of our matrix here, we can see the output or feature map, it is 4 by 4. So it is 4 by 4. That means we can see there is 4 by 4. So that means from the 6 by 6 image, if we apply 3 by 3 filter, considering the straight one and no padding, then we will get 4 by 4. That means the output size. Then how can we determine the output size for different setups? Like if we have 10 by 10 image, if we apply 5 by 5 filter, and if we apply a straight 2 uh, with padding, then what will be the output for that? What will be the feature map size for that? Okay. Uh, so the output after the convolution operation, it will depend on the several parameters. Okay. So here, at first, we need to think about there is the padding and also the straight. And we have to have already that is the image size and also kernel size. So here the padding can be, usually we can say that padding can be the same, it can be valid, it can be full. So 3 kinds of padding. So same, it means add zero padding to the image to have the output of the same size as m by m. So the same, it means we want the same size of output as the image size. So for that, what we have to do, we have to apply the zero padding. We have to apply the zero padding. That then the output size will be the m by m. That means m by m is image size and output size will be the m by m. Then valid, in this case, with no zero padding, kernel is restricted to traverse only within the image, and the output size will be this. So what does it mean? It means the m is our the m is our dimension of our image. Okay, so m is image dimension, and the k is our kernel size. The kernel size, that means usually we have considered here this 3 by 3 plus 1 times m minus k plus 1. Okay, and full here is add zero padding to the image enough for every pixel to be visited k times in each direction. Okay, on that case, the output size will be m plus k minus 1 and m plus k minus 1. So this will be the output size. That means for the padding, we have 3 options: same, valid, and full. And for each and every case, the image size will be different. And here is the straight. So these calculations, we have considered the straight equal 1. So here the straight, it is downsampling of the output convolution by sampling only with every s pixels in each direction. Okay, so the straight, and if we consider the different straight, like if we consider a straight 2, that means it will shift 2 bits for that, both in that is right shifting and down shifting. Okay, uh, so on that case the output size will be, for if we set up the valid padding, and then based on the straight size, the output image size will be this, output feature size will be this. The feature map size will be m minus k plus s divided by s and m minus k plus s divided by s. Okay, so this will be our output size based on the different setups of a straight. And here is the for the valid padding. Okay, for the valid padding. So here we can see that if we consider padding equals same, sorry. So padding equals same. On that case, we can see that is the we have to consider the zero padding. The original image is actually, this is the original image. So original image size is what? It is 1, 2, 3, 4. That means 4 by 4. 4 by 4. Original image size is 4 by 4. 4 by 4. And then we want the same dimension, okay? Same dimensional feature maps. On that case, what we have to do, we have to apply the zero padding. You can see that 0, here is also 0. Okay, these are added zero padding. Here is also zeros, and also zeros are there. So we have added those, and after that we can see here the filter size is 2 by 2. In this case, 2 by 2. There is filter size is 2 by 2. 2 by 2. If we apply the convolution here, in this case, like 0 times 0, 1 times 0, and 0 times 0, and here is the 0 times 0, and 0.5 times 1, that means we will get 0.5. Here is the 0.5. Okay, so in this way we will get this output. That is our, for the case of the padding same. And for the case of the padding valid, we can see in this case, so considering straight equal s equal 1, s equal 1, on that case, we can see here that is the output size will be, according to our equation, it is m minus of k plus of 1. So this will be the size. Okay? This will be the size of output. So in this case, we can see here m is what? M is, for this image, m is like 4 by 4. 4 by 4. So m is 4. Then what's the kernel size here? Kernel is 2 by 2. 2 by 2 kernel. So that means k is 2 plus 1. Okay. So in this case, that means 4 minus 2 plus 1. 4 minus 2 is 2. 2 plus 1 is 1. That is 3. You can see we have the output 3 by 3. Okay. So that means for the padding equal valid, we will have the output this one. Now what we have to do, the next thing we need to consider about, that is our convolution versus fully connected. So as at the beginning of this lecture, I have discussed that actually what's the benefit of the convolution operation over our traditional fully connected neural networks, or you can say deep neural network architecture. So we need to understand the benefits. So we can see, if we consider this image, we have already considered this image. This is a 6 by 6 image. Okay, 6 by 6 image, 6 by 6 image, and we have considered the filter one. This is our filter one, and this is our filter two, kind of the bake detector and wing detector. Okay, and after applying filter one, we got our 4 by 4 output, the background one. And after applying the filter 2, we got for 4 by 4 output, and that is our the front one. Okay, this feature map we got. Now if we consider our fully connected neural network, so for fully connected network, if we want to feed this to our neural networks, then here is this 6 by 6 image. So 6 by 6 image, how many neurons we have to consider at the input layer. So we can see here 6 by 6. That means we can see total 36 values are there. 6 by 6 means 36. Okay, 6 into 6, that is 36. 36 values are there. So for each and every value, we have to feed this value to our neurons. Okay, so that means we have to have 36 neurons in our first layer. Okay, so here is it. We can consider like x1, x2 up to x36. Okay, so x1 is in this case 1, x2 is in this case 0, and then x3 is 0, like this way. Okay, like this way. So now if we consider that actually we have also the same number of neurons in our first hidden layer. Okay? So this is our hidden layer. Hidden layer. Consider first hidden layer here. And we can see here there is for each and every neuron we have to connect to every neurons of our hidden layers. Every neurons of our hidden layers. So in this case, we can see here there is. So now, if we want to represent the convolutional neural network output, convolutional neural network output. So this is a filter one, first filter. We perform the convolution operation in first batch, and then we got this output. So now we can see in this case, actually here is this the input in this case. So 1, then 0, then 0, and then 0, like this way. So in this case, we can see this is 1, then 0, 0. So in this case, we can see 1 and 0 and 0. And then fourth position is also 0. The total we can see 1, 2, 3, 4, 5, like 4. So this is our 7, 8, 9, 10. Then this is the 13 and 14, 15, 16. Okay. So we have also here the 5 and 6. So in our 5, this is 4, 4 is 0, 5 is also 0. 5 is 0. And 6, I don't know, the 6, here the 6 is 1. That is this value. So 6 is 1. Okay, 6 is 1. 7, 0, 8, 8, 1, then 9, 0, 10, 0, then 11, and then 12. So for the 11, we can see 6, this is 7, this is 8, this is 9, this is 10, then 11 is 1. Okay, so 11, in 11 we have this 1 in our input. So here is the input 11, and for the 12 we can see sorry, 12 is 0. Okay, 12 is 0. 12, in this case we will get 0 here. 13 is 0, 14 0, 15 0, 16 0, and then 17 we can see here 17. For the 17, 12, 13, 14, 15, 16, 17 is 0. Okay, 17 is also 0. So if we can see here, so here is 0. Now we can see that means we can see here is the 3. Here is the 3. That means if we perform the first convolution operation for this filter and for the first batch, these are connected to this value. That is the value 3. Okay, so if we consider that there is for each and every values we have like the input. This is our input layer. This is our input layer. This is our input layer, and we have like 36 inputs from our input layer, and then it is connected to this hidden layer. That means this is the value. This is one neuron. Now we can see that actually for the convolution operation, for performing the convolution operation, uh, this value, the first value of the filter 1 is connected to our uh, to compute these values. Okay, so that means we can see this 1 is used. Sorry, this 1 is used there. So that means this 1, the value 1 is used there, and then value number 2 is also used there. So here this one is used there, and then value number 3 is also used there. So that means 3 is used there, and then we can see here that the 5 is not used. Sorry, 4 is not used, 5 is not used for calculating our fast feature values. So 4 is not used, and then we can see that is 7 is used, 8 is used, and 9 is used. So here we can see 7, 8, and 9, and that's why you can see that the lines are there. Okay, there is connection is there, edges are there, and then 12, then 13, 14, and 15, those values are used there. So here is the 13, 14, and 15, those values. Those values are used to calculate what? To calculate these neuron values. Okay, these neurons values. And now we can see that that is instead of the full connection, full connection, like we have to connect from each and every neurons of our input image to our hidden layer values. But we can see only selected values are here used, like 1, 0, 0, and then 7, 8, 9, and then 13, 14, and 15. That means we can see we have reduced the connections, reduce the connections. Okay, so we can see only connect to the 9 inputs, not the fully connected. Okay, so instead for this model we can see there is, you can see for each and every input we have to connect all the 36, but here we have connected only 9. Okay, only 9. That means lots of connections are already reduced in our convolution operation. And then what other benefits we have here? Okay, now we can see that uh, for in computing our next value, like there is that -1. So actually we shifted our pass using the straight one, and then again we do the operation. We do the operation. So in this case, we can see that is these are the values. So we can see 0, 1. So that means 2, 3, 4, and then 8, 9, and 10, and then 14, 15, and 16. Those are the values we have to use here. That means this time also 9 connections. But what we can see, that means we use the same filter. That means this weight we have also used here to calculate this one. So this weight, there is the filter number 2. This weight we have to use, we have already used there. That means we can say these are the shared connections, shared weights. So the same weight we have uh, used for calculating this 3, and same weight we have used for the calculation of the negative one also. And that's why you can see we use the same color. That means the same weight, same weight. The same weight are used to calculate these things. It means that the shared weights are there. Shared weights are there. That means same weight, the same weight we have to calculate the feature values or feature maps values using the same weight. So in this case, we can see that is this 3, and then this -1, and then this -3, and then this -1. Actually, we will use this the same weight, okay, to calculate all these values. So the number of parameters will reduce in case of convolutional neural networks. Number of parameters will reduce. So we will uh, in our we have already seen this one, so we can say convolution. What we have to do after convolution, we have to apply the pooling operation. Okay, so in our next class we will start from here, that is how to perform the pooling operation, and then maybe uh, the rest of the things. So any question from your side?
Sir, are we going to have an extra class tomorrow?
Extra class tomorrow? No, maybe a Saturday.
No, like we got an email saying that Fridays, like the next Friday will follow the Thursday, Saturday routine from the registrar office. 2 days ago.
Okay. Um, uh, I don't know whether I received that email or not. Okay, there will be no extra class.
All
We
right.
will actually, yeah, we have a class on Saturday. And so I hope you all submitted the assignment. Okay,
Yes,
thank
sir.
you. Thanks everyone.
Thank you, sir.
Thanks everyone. Okay, see you in our next
Assalamu
Thank you,
class
alaikum,
sir.
sir.
on Saturday. Walaikum salam.
Assalamualaikum, sir.
Assalamualaikum, sir.
Walaikum salam.